Welcome dear learners. We are continuing quantum chemistry. In this module, we are discussing molecular orbital diagram of homonuclear diatomic molecules. The contents of this module are the molecular orbital theory, molecular orbital diagrams of homonuclear diatomic molecules, exceptional arrangement, bond order and stability, illustration of molecular orbital diagrams and problems. First of all, molecular orbital theory. We heard about the concept of molecular orbital theory. The molecular orbital theory was developed by F. Hunt, R. S. Mulliken and J. E. Leonard Jones in the year between 1927 and 1932. Molecular orbital theory is very simple to treat mathematically and it is a landmark in molecular quantum mechanics. Just as atomic orbitals are the solutions of the time-independent Schrodinger wave equation for atoms, the molecular orbitals are corresponding solutions for molecules. According to linear combination of atomic orbital approach in molecular orbital theory, when atomic orbitals come close together, they overlap to form molecular orbitals. Thus, the molecular orbital wave functions are obtained by the linear combination of atomic orbital wave functions. The linear combination of atomic orbital wave functions may be addition combination or subtraction combination. We can now simply illustrate the linear combination of atomic orbital wave functions and we can proceed like this. First of all, we can take the oneness orbital. The oneness orbital can be represented the wave function psi of oneness. When two psi oneness atomic orbital wave functions added together, we are getting psi of sigma oneness. Here, psi of sigma oneness is the molecular orbital wave function corresponds to the molecular orbital sigma oneness. Here there is a positive sign and it simply represents linear addition combination. We can represent the subtraction combination of oneness atomic orbital wave function like this. Psi of oneness minus psi of oneness gives a psi of sigma star oneness. And here I am putting sigma star. This is because sigma star oneness is the antibonding molecular orbital. And the antibonding molecular orbital wave functions are obtained by the subtraction combination of atomic orbital wave function. In a similar way, we can also represent the linear combination of 2s orbital wave functions like this. Psi of 2s plus psi of 2s, this is linear addition combination, you are getting psi of sigma 2s. Psi of 2s minus psi of 2s, you are getting psi of sigma star 2s. This is addition and subtraction combination respectively. We can also consider the linear combination of 2p atomic orbitals. 2p atomic orbitals are 3 in number, namely 2px, 2py and 2pz. Let us assume that the end-to-end overlapping happens through the z axis and z is considered to be the internuclear axis. We can consider the formation of the sigma molecular orbital by the overlapping of 2 sigma 2pz orbitals, 2pz orbitals. So, we can represent the linear combination of the 2pz atomic orbital wave function by using this expression. Psi of 2pz plus psi of 2pz, you are getting psi of sigma 2pz. Psi of 2pz minus psi of 2pz, you are getting psi of sigma star 2pz. The second one represents subtraction combination of 2pz atomic orbital wave function. Whereas the first one represents, this one represents the addition combination of 2pz atomic orbital wave functions. Similarly, there are two more atomic orbitals, namely the 2px and 2py wave functions. That is psi of 2px plus psi of 2px. You are getting psi of pi 2px. Here I am putting pi molecular orbital. This is because pi molecular orbitals are produced by the lateral overlap of atomic orbital. End-to-end overlap happens through the z axis and hence the molecular orbital formed is sigma and sigma star. lateral overlap may occur through x direction or y direction. Therefore, we are getting pi 2px, pi 2py, pi star 2px and pi star 2py, and the linear combination can be represented like this. This is linear addition combination of two 2px atomic orbitals, and psi of 2px minus psi of 2px, we are getting psi of pi star 2px, and finally psi of 2py plus psi of 2py gives psi of pi 2py, psi of 2py minus psi of 2py gives psi of pi star 2py. These are 10 molecular orbital wave functions which are produced through the linear combination of atomic orbital wave functions. Thus, it is clear that the molecular orbital theory gives emphasis to linear combination of atomic orbital wave functions to get molecular orbital wave functions. Addition combination leads it to bonding molecular orbital wave function. Subtraction combination leads it to anti-bonding molecular orbital wave function. Now, two atomic orbitals can overlap to form molecular orbital. Now the question arises, what is the difference between the linear combination and overlap? Overlap always gives us a physical picture, but linear combination gives us a mathematical picture. What we discussed here is linear combination, and we are now considering the overlapping. When two oneness orbital overlap, they will form, addition overlap will form sigma molecular orbital or sigma oneness, and subtraction overlap leads to sigma star oneness. So, overlapping gives us a physical representation or physical picture, and linear combination represents a mathematical idea behind the principle. Now, one of which lies at lower energy, this molecular orbital, among the two molecular orbitals, one of which lies at a lower energy level than overlapping atomic orbital and is called bonding molecular orbital. The other orbital which lies at a higher energy level and is called anti-bonding molecular orbital. So, when two atomic orbitals undergo overlap, we are getting two molecular orbital, one of which is having lower energy than atomic orbital and other one is having higher energy than atomic orbital. Those with the lower energy is called BMO, and other one with the high energy is termed as anti-bonding molecular orbital or ABMO. Now, overlapping of atomic orbitals, I already mentioned the fact that it gives us a physical picture. Now we are representing the overlapping of two oneness atomic orbitals. Two atomic orbitals can overlap to form two molecular orbital. End-to-end overlap leads to sigma molecular orbital, whereas lateral or sidewise overlap leads to the formation of pi molecular orbitals. This is the pictorial illustration of overlapping of two oneness orbitals. This is the first oneness orbital, this one is the second oneness orbital. They will overlap together to produce sigma oneness with low energy and sigma star oneness with the high energy. So, this is the physical representation or physical picture. So, that I already mentioned, overlapping represents a physical picture of the molecular orbitals and atomic and the participating atomic orbitals. So, this is about the overlapping of oneness atomic orbitals. Now, the 2s orbitals of one atom combine with the 2s orbital of other to form sigma 2s and sigma star 2s. This is analogous to overlapping between two oneness orbitals. So, similar to oneness orbital, two oneness orbital undergo overlapping to produce bonding molecular orbital, that is sigma 2s, and antibonding molecular orbital sigma star 2s. Antibonding molecular orbital, just like sigma oneness and sigma star oneness, formed from the oneness atomic orbitals. This means the overlapping of two 2s orbitals are similar to the overlapping of two oneness orbitals. Now, we are considering the overlapping between 2p orbitals. We know there are 3 p orbitals, namely px, py and pz. Now we take the assumption that end-to-end overlap happens between 2 pz orbitals, and this leads to the formation of sigma 2 pz, which is bonding molecular orbital, and the sigma star 2 pz, which is anti-bonding molecular orbital. This is the pictorial illustration of end-to-end overlap between 2 pz orbitals to form sigma 2 pz bonding MO and sigma star 2 pz anti-bonding MO. Now, lateral overlap between 2px orbital of adjacent atoms leads to the formation of pi 2px, which is BMO, and pi star 2px, which is anti-bonding MO. This is the pictorial representation of the overlapping between 2px orbital, which is lateral or sidewise overlap, to form pi 2px, that is bonding molecular orbital, and pi star 2px, which is anti-bonding molecular orbital. Similarly, the lateral overlap also happens between 2py orbitals of adjacent atoms, and that leads to the generation of pi 2py bonding MO and pi star 2py anti-bonding MO. That all about complete overlapping of atomic orbitals to form first 10 molecular orbitals. Each molecular orbital can hold 2 electrons in accordance with the Pauli's exclusion principle. As per the Pauli's exclusion principle, no 2 electrons in an atom can have all same set of 4 quantum numbers. That is a very important principle related to electronic arrangement or electronic configuration. And these 2 electrons must have opposite spin also. Similar to atomic orbital, each molecular orbital can also hold only maximum of 2 electrons. Now, it is possible to construct an energy level diagram by accommodating various molecular orbitals in the increasing order of their energy. Such a diagram is called MO diagram or the molecular orbital diagram. And all the rules of electronic configuration are applicable to molecular orbital diagrams also, or molecular orbitals also. Now, 2 important concepts we are discussing here is the paramagnetic feature and stability. If the molecular orbital contains some unpaired electrons or at least one unpaired electron, then the molecule will be paramagnetic. Otherwise, the molecule will be diamagnetic. You should know the fact that paramagnetism arises due to the presence of the unpaired electrons. So, in molecular orbital diagram, if you are analyzing the MO diagram, if we can see at least one unpaired electron in any one of the molecular orbital, you can say that the molecule will be paramagnetic. Otherwise, the molecule will be diamagnetic. The ordering of molecular energy levels can be verified experimentally also, and the technique used for this experimental verification is a spectroscopy technique, and that spectroscopy technique is known as the photoelectron spectroscopy. Now, we are discussing molecular orbital diagrams of homonuclear diatomic molecules. This is the important part of the present discussion. What are homonuclear diatomic molecules? In a diatomic molecule, if the participating atoms are similar, you can call it as a homonuclear diatomic molecule. Several examples are there: H2, N2, O2, F2, Br2, I2, like that. All are nice examples for homonuclear diatomic molecules. And we are now discussing MO diagram of homonuclear diatomic molecules. We know the fact that overlapping of atomic orbital or linear combination of atomic orbital may lead to molecular orbitals or molecular orbital wave functions. We previously just heard about the overlapping of atomic orbitals to get 10 molecular orbitals, out of which 5 are bonding and 5 are anti-bonding. So, we familiarized the formation of first 10 molecular orbitals. They are sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, sigma star 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py. These are 10 molecular orbitals, the formation of which we discussed just earlier. Now, it is possible to arrange these molecular orbitals in the increasing order of their energy to get a diagram, and that diagram is termed as energy level diagram or the molecular orbital diagram. This molecular orbital diagram for homonuclear diatomic molecule is the present part of the discussion, and now I am representing the MO diagram of homonuclear diatomic molecules. I already mentioned the fact that the MO diagram is an energy level diagram. So, we have to place molecular orbitals in the increasing order of their energy. This is being an energy level diagram, and in order to represent the MO diagram or molecular orbitals, we have to represent atomic orbitals also, because atomic orbitals are responsible for the formation of molecular orbitals. So, in left side and right side of this MO diagram, I am putting atomic orbitals of the participating atoms. So, the lowest, this left part is atomic orbitals, AOs, right side is also atomic orbitals, and the middle portion represents the molecular orbitals. The lowest energy atomic orbital is 1s. So, this is 1s of the second atom. I mark it as 1s. This is 1s. After 1s, I will have a 2s orbital. This is 2s. This is also 2s. Keep the energy level should be same. This is because of the fact that the participating atoms are same, because we are discussing a MO diagram of homonuclear diatomic molecules. So, 2s of the first atom should be in the same energy level with that of the second atom. Now, I have to represent the 2p atomic orbital. There are 3 2p atomic orbital. They are namely 2p, x, y and z. Here also I am putting 2px, 2py and 2pz. This is 2p, x, y and z. Now, we have to represent the molecular orbitals. First of all, 1s orbital combine together to produce the molecular orbital. This is sigma 1s with the low energy, and this one is sigma star 1s with the high energy. I can represent a connection mark like this, and this is the situation. This about sigma 1s and sigma star 1s. Similar to this, here there is the formation of sigma 2s, and its antibonding level is sigma star 2s. Here also I can connect it with the help of a line. This about the situation. This is sigma 2s, this is sigma star 2s, and now we are mentioning the overlapping of the 2pz orbitals. 2pz will combine together to produce sigma 2pz. Its antibonding level is at the high energy position, that is sigma star 2pz. Then lateral overlap of 2px and 2py leads to the formation of doubly degenerate levels. They are pi 2px and this level is pi 2py. This is the antibonding level. It is nothing but pi star 2px and pi star 2py. This about here also I can make it some connection lines to show that they are mutually connected, or atomic orbitals are responsible for the formation of molecular orbitals. This is about the simplest form of the MO diagram of homonuclear diatomic molecules. This is the representation. The MO, we can use a square or circles as your convenience, or simple line is also sufficient. The molecular orbital diagram for homonuclear diatomic molecules with regular energy order is shown. This is 1s, 2s, 2p, they are atomic orbital. These are atomic orbitals of the first atom. These are atomic orbitals of the second atom, and they combine together to produce the molecular orbitals of the molecule. They are shown at the middle. This is about the MO diagram for diatomic molecules, homonuclear diatomic molecules without any exceptional order, or this is the regular energy order. The energy order is lowest energy is sigma 1s and highest energy is sigma star 2pz. Thus, the regular energy order of 10 molecular orbitals is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Then a doubly degenerate level, 2 orbitals have the same energy. They are pi 2px equal to pi 2py, pi star 2px equal to pi star 2py, and the highest energy orbital sigma star 2pz. This about energy order of first 10 molecular orbitals, regular energy order. Now, we are discussing some exceptional arrangement. It should be noted that in the case of second row elements of the periodic table, second row elements means beryllium, boron, carbon, nitrogen. In the case of second row elements up to nitrogen, lithium, beryllium, boron, carbon up to nitrogen. For these elements, the energy of the sigma 2p z orbital, energy of the sigma 2p z orbital is slightly higher than doubly degenerate orbitals pi 2px and pi 2py. This is the slight correction. Hence, we can rewrite the energy levels of these molecules as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py, sigma 2pz, pi star 2px equal to pi star 2py, and sigma star 2pz. So, there is a jump. The position of sigma 2pz is just above pi 2px and pi 2py. That is an exceptional arrangement. This arrangement is noted in the case of second row elements of the periodic table up to nitrogen. So, such elements are lithium, beryllium, boron, carbon and nitrogen. Now, we are discussing another important parameter, that is called bond order. Bond order is a measure of stability. The important advantage of molecular orbital theory above valence bond theory is that the MO theory can assess the stability of the molecule, and that stability assessment is based on a parameter called bond order. After obtaining the MO configuration from molecular orbital diagram of molecules and ions, we can calculate a parameter called bond order of the system. The bond order is defined as 1/2 of the difference between number of electrons present in bonding orbitals and that present in antibonding orbital. So, bond order equal to half of Nb minus Na. Nb represents bonding electrons, electrons present in bonding orbital, and Na represents antibonding electrons, electrons present in antibonding molecular orbitals. So, we have to take the difference and divide by 2 to get a quantity. That quantity is called bond order. Bond order has a strong connection with the stability. Many information we will get from bond order also. What are such informations? Bond order helps us to understand the stability of the molecules. Higher the bond order, higher will be the stability, and a zero value of bond order indicates that the molecule is highly unstable or that molecule is not formed. Now, bond order gives number of bond present between atoms. That is very, very important. For example, if we can take a nitrogen molecule, we will get the bond order as 3. That means in nitrogen molecule, there exists a triple bond between two nitrogen atoms. For oxygen molecule, the bond order value can be calculated as 2, and that means a double bond exists between two oxygen atoms. So, bond order gives the number of bond present between atoms in a molecule. Now, higher the bond order, shorter will be the bond length. This is most important observation. Higher the bond order, shorter will be the bond length. So, bond order increases, number of bond present between atoms increases. So, they will come more close to each other, and as a result, there is a diminishing or decreasing in the bond length is observed. Now, illustration of molecular orbital diagrams. Now, we are going to illustrate some MO diagrams by taking simple examples, simple homonuclear diatomic molecules. First of all, MO diagrams of H2 and H2 plus. It should be noted that H2 plus is the simplest molecule. Here 2 hydrogen atoms are there, but one hydrogen acts as H plus. So, it is an one electron system. And we are now comparing or discussing the molecular orbital diagrams of H2 and H2 plus. First of all, we can take the case of hydrogen molecule. Hydrogen molecule is obtained by the combination of two hydrogen atoms to get H2. The first hydrogen is having a configuration 1s1, second one is also having 1s1. So, this is first hydrogen, this is atomic orbital of hydrogen, this is atomic orbital of hydrogen, here also 1s1. So, the middle part is molecular orbital of H2. So, in H2 there are 1 plus 1, there are 2 electrons. So, these 2 electrons are present here. and the MO configuration of hydrogen molecule is sigma 1s2, sigma 1s2, and for hydrogen bond order is, in antibonding there are no electrons and bond order is 2 minus number of antibonding electron is equal to 0, number of bonding electron is equal to 2. So 2 minus 0 divided by 2, that is equal to 1. It means there exists a single bond between two hydrogen atoms. This about the MO diagram of hydrogen molecule. Now we can take MO diagram of H2 plus. H2 plus is generated by the formation of hydrogen and another H plus to get H2. In hydrogen, the electron arrangement is 1s1. So this is atomic orbital of hydrogen. This is 1s1. But in H plus there are no electrons, so you need not to fill electrons in 1s orbital. So H2 plus is an only one electron molecule, and that one electron is accommodated here. Therefore, the MO configuration of H2 plus is sigma 1s1. Sigma 1s1. Then what will be the bond order? 1 minus number of antibonding electron is equal to 0 divided by 2, that is equal to half. Since bond order is a positive quantity, this molecule may exist. It is not unstable. It may exist. It may exist. A 0 value of bond order indicates that the molecule will not exist or highly unstable. So this part sigma 1s2 is the MO configuration or a MO configuration of H2, and the sigma 1s1 is the MO configuration of H2 plus. That all about the MO diagrams of H2 and H2 plus. Now we can take MO diagram of oxygen molecule. First of all, this is the template, this is the diagram, and we have to fill electrons in this MO diagram. We know the fact that two oxygen atoms combine together to produce O2 molecule. In the first oxygen, the electronic configuration is 1s2, 2s2, 2p4. And here there are a total of 8 electrons. Here are also 8 electrons. Total number of electrons is equal to 60. So I have to accommodate 16 electrons in the MO diagrams for O2 molecule, and I can do it like this. First of all, this is the atomic orbital of oxygen. This is atomic orbital of second oxygen. This middle portion is molecular orbitals of O2 molecule. So oxygen has arrangement 1s2, 2s2, 2p1, 2, 3, 4. Similarly, for the second oxygen atom, the arrangement is 1s2, 2s2, 2p1, 2, 3, 4. So atomic orbitals are now completed. These atomic orbitals combine together to produce the molecular orbital, and the molecular orbital consists of 16 electrons. So the arrangement is like this: sigma 1s2, 2s1, sigma star 1s2, sigma 2s2, sigma star 2s2, 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this about molecular orbital diagram of oxygen molecule. Now I can represent the MO configuration of oxygen molecule as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2 equal to pi 2p y2, pi star 2p x1 equal to pi star 2p y1. Here you can see the presence of two unpaired electrons in the MO diagram. Absolutely no doubt, as a result of these two unpaired electrons, oxygen molecule definitely exhibit the phenomenon of paramagnetism. Oxygen molecule shows paramagnetism. Now we have to calculate the bond order of the system. We have to find out the number of bonding electrons: 2, 4, 6, 8, 10. So here there are 10 bonding electrons, and remaining will be 6 will be antibonding electron. So bond order is equal to 10 minus 6 by 2, that is 4 by 2, that is equal to 2, which simply implies that a double bond exists between oxygen atoms. This about MO diagram of oxygen molecule. Now we can consider MO diagram of O2 plus. We have to make a small change. How O2 plus is obtained? O plus gives O2. In oxygen there are 8 electrons. In O plus there is only 7 electrons. So O2 plus is a molecule having 15 electrons. So this is atomic orbital of oxygen. This is atomic orbital of oxygen plus. This is molecular orbital of O2 plus. Atomic orbital of oxygen has configuration 1s2, 2s2, 2p, 1, 1, 2, 3, 4. Here there is 1s2, 2s2, 2p, 1, 2 and 3. So 8 and 7 we have to fill 15 electrons and the configuration is 2, 4, 6, 8, 10, 11, 12, 13, 14 and 15. So the MO configuration is somewhat similar to that of oxygen molecule, but it lacks 1 electron, and the MO configuration will be like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2 equal to pi 2p y2, and finally pi star 2p x1 or y1. So the bond order will be 10 minus 5 by 2 and that is equal to 2.5. Again you can see the presence of one unpaired electron here in the MO diagram, and the O2 plus molecule is again a paramagnetic molecule. Thus the conversion of O2 plus or the formation of O2 plus from O2 causes an increase in the bond length from 2 to 2.5. In oxygen, the bond order is 2, and in O2 plus, the bond order is 2.5. That is an important thing to be noticed. Now, we are discussing MO diagram of nitrogen. This is the MO diagram of nitrogen. Here we can see left side is atomic orbital of nitrogen atom. This is atomic orbital of second nitrogen atom. The center portion represents the molecular orbitals of nitrogen molecule, and this is the MO configuration. And whenever you are looking this MO configuration, you cannot see any unpaired electrons here, but you noticed the exceptional order. Energy of the sigma 2p z orbital is slightly higher than that of pi 2px and pi 2py. That is an important thing, because in the case of second row elements up to nitrogen, there is an exceptional energy arrangement. Energy of the sigma 2p z orbital is slightly higher than that of pi 2px and pi 2py. So whenever we are evaluating the bond order, we will get the bond order value is equal to 10 bonding electrons minus 4 anti-bonding electrons divided by 2, that is 6 by 2, that is equal to 3. That simply means a triple bond exists between two nitrogen atoms. Since the molecular orbitals contain no unpaired electrons, we need not to consider atomic orbital, we have to look only molecular orbital to assess the paramagnetic behavior. And in the molecular orbital, there are no unpaired electrons, and we can say that the nitrogen molecule is a diamagnetic molecule. Nitrogen is diamagnetic. This is because there is no unpaired electron present in the molecular orbitals. Now we know the configuration and all other arrangement. Finally, we are moving on to some simple problems based on the molecular orbital theory. The first question is why helium-2 is not formed. We know about helium having configuration 1s2. So He2 can be theoretically formed by the combination of two helium atoms. So here 2 electrons, here also 2 electrons. So in He2 we have to accommodate 4 electrons. We have to accommodate a total of 4 electrons, and the MO configuration must be sigma 1s2, sigma star 1s2. Sigma 1s2, sigma star 1s2. So the bond order of the system will be 2 minus 2 divided by 2, that is equal to 0. A 0 value of bond order indicates that the molecule is not formed or highly unstable. So He2 is not existing. And we are now considering the MO configuration of N2 plus, calculate bond order and predict magnetic behavior. We know the MO configuration of nitrogen as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz is having high energy than pi 2px and pi 2py. So I have to mention pi 2px equal to pi 2py first prior to sigma 2pz. So 2, 4, 6, 8, 10, 12, and if it is nitrogen, there are 14 electrons. Therefore, the configuration will be sigma 2pz2 for nitrogen. But we are having N2 plus. N2 plus lacks 1 electron compared to nitrogen. So here there is only 1 electron. Now we have to calculate bond order of N2 plus. In N2 there are total 13 electrons, out of which 2, 4, 6, 8, 9. 9 electrons are present in bonding molecular orbital and 4 electrons are present in anti-bonding molecular orbital. Therefore, bond order is equal to 9 minus 4 by 2, that is 5 by 2, that is 2.5. Now, we have to predict the magnetic behavior of N2 plus. In N2 plus, you can see the presence of one unpaired electron, which is present in sigma 2pz orbital. So N2 plus molecule is paramagnetic, but N2 is diamagnetic. Now the last problem, arrange these 5 species in the increasing order of stability. In order to solve this, we have to first write down the MO configuration and evaluate bond order. We can arrange these species in the increasing order of bond order. Higher the bond order, higher will be the stability. In order to easily solve these problems, I will give you a chart, and that chart illustrate a relation between number of electrons and the bond order. And this is the chart. From 14 to 20 number of electrons are shown here, and the bond order values are also here. Number of electrons increases, bond order decreases from 3, 2.5 to etc. etc. Now we can fit these molecules in by looking this chart in the order of stability. For O2 there are 16 electrons. For O2 plus there are 15 electrons. For O2 2 plus there are only 14. For O2 minus there is 17 electrons, and for O2 2 minus there are 18 electrons. For O2 2 minus the bond order is 1, and for O2 minus 17 electron bond order is equal to 1.5. For O2 2 plus bond order is equal to 3, and for O2 plus bond order is equal to 2.5, and for oxygen bond order is equal to 2. Hence the stability order is like this: O2 2 minus less than, O2 minus less than, O2 less than, O2 plus less than, O2 2 plus. This is about the stability order of the given 5 species based on bond order. This chart is highly useful as far as different competitive examinations are concerned. Hence, in this module, we have studied about the MO diagram of homonuclear diatomic molecules with relevant examples and problems. That all about the present module. Have a nice learning experience. Thank you.